Okay, we're pleased to have Ed Hansen back with us for the final part of his climate change trilogy, I guess you'd call it. We've been kind of walking through the last few billion years of climate change, and Ed is now going to tell us um, what our understanding of ancient climate change may do to understand future climate change. So Ed, it's all yours.
Okay, so now we're going to look at the next 100 years. But first, I just want to do a basic review. Recall that instrumental temperature readings for the land surface over the last 20 years shows over the last 150 years appear to show a warming trend which has accelerated over the last 50 years. Okay, we've talked a lot about this. What we haven't talked about very much is this. This is CO2 measurements taken at Mauna Loa. The reason they chose Mauna Loa to monitor CO2 is that it's pretty isolated. If anybody's ever been on the Big Island of Hawaii, there's almost no industry, not even all that much traffic. So there are very few local sources of CO2, and particularly when you get to the high observatory. Um, it's relatively isolated from local anthropogenic effects. So it's a good place to look at global changes. We started doing that in the late 50s. First of all, the red line shows the shows monthly averages, and they go up and down. Anybody know why? What part of the year do we have higher CO2, and what part of the year do we have lower CO2? Yeah, this is simply photosynthesis, the fact that plants use carbon dioxide to create organic molecules that eventually create energy. So when plants are active in the summer, CO2 levels go down. In the winter, CO2 levels go up. I'm I should give you a bit of a warning. I just went to the eye doctor for what we thought might require emergency surgery, which it doesn't, but my eyes are dilated and my balance is a little off. So, but no, there's this up and down trend. But if you take yearly averages, there's this constant trend with increasing CO2 in the atmosphere. And that's clear. It actually came as somewhat of a surprise. I know in the late 50s, there was a debate about whether we were changing the amount of carbon dioxide in the atmosphere. And one side of the debate said the atmosphere is just so large, our emissions are relatively small. It shouldn't have much of an effect. Now, combustion. Most of our energy comes from the combustion of fossil fuels. And here's natural gas. You take methane, natural gas, you add oxygen, and you get carbon dioxide and H2O. And it doesn't matter whether it's methane or liquid petroleum or coal, every burning of every fossil fuel produces carbon dioxide. It oxidizes reduced carbon. So burning the fossil fuels increases the amount of CO2 in the atmosphere. Now, during photosynthesis, as we've already referred to, the very opposite happens. Plants grab carbon dioxide, combine it with water, and use sunlight to form organic compounds. So plants remove CO2 from the atmosphere. They're not the only thing. Some CO2 gets absorbed in the oceans, for example, but the primary way to remove CO2 from the atmosphere is through photosynthesis. And that means that tropical deforestation or deforestation in general has two effects. Burning of plants. Well, you burn the plant material, you oxidize it, you produce CO2, and the less plants you have means that less CO2 is removed. So deforestation can also add to the amount of CO2. So can reforestation, and this is an aside. One of the problems with the carbon cycle, and one in geochemistry where I taught the carbon cycle in detail, is the fact of what they call the missing sink. There's less CO2 in the atmosphere than there should be, considering the amount that we have. And it seems to me more and more likely that what we're seeing is an increase in the amount of vegetation, not in the tropics, but outside the tropics. And that's part of the missing sink. That's one of the reasons why we have some of the CO2 we're adding to the atmosphere is unaccounted for. So reforestation can do the opposite. It can remove more CO2. Okay, so there's no doubt that the increase in CO2 in the atmosphere is due to human activities. In this graph, this is our total amount of emissions. Okay, that's how much we're adding to the atmosphere. If you take a look at the amount that's sticking around, take a look at bubbles in glacial ice. Here it is. And it follows more this roughly 50%, I guess 46% of total emissions. So very roughly half of the CO2 that we're putting in the atmosphere stays in the atmosphere. The other half is removed by various mechanisms. And this in itself should be fairly convincing, but the clincher is that isotopically, fossil fuels have a different carbon isotope composition. That's because they all originated in photosynthesis. And photosynthesis prefers light carbon versus heavy carbon. So they're all light in carbon, carbon-12 versus carbon-13. And if you look at the way the isotope compositions of carbon dioxide in the atmosphere is changing, it looks more and more like fossil fuel carbon isotopes. So, concern over the possibility of global warming led the World Meteorological Organization, from which I think we've just withdrawn, and the United Nations Environmental Program to create something called the Intergovernmental Panel on Climate Change, the IPCC. And we'll be referring a lot to the IPCC. It formed in 1988, not that long ago, although I guess my third year of teaching at Hope College. The IPCC is broken into a number of working groups. Working Group 1 is composed of natural scientists, and it is their purpose to assess scientific information on climate change. Now, I don't know any of the IPCC panel members well, but I do know a couple of them, and they're all in Working Group 1. I casually know a few of them. Working Group 2, natural scientists and social scientists assess likely environmental and socioeconomic impacts of climate change. And those are the only two working groups we're going to look at as results from those two. There's also Working Group 3, non-scientists who formulate responses. So these are the people who decide what should we do about this. The Paris Accords, for example, are their work. And a task force to oversee the IPCC National Greenhouse Gas Inventories Program. So that's how they're organized. In every 5 to 6 years, the IPCC and its working groups produce a series of reports called assessments, which summarize our current information on climate change. So when I was teaching, the problem is every new assessment comes out and I have to change. Not that anything's drastically different, but you look at the latest information, including the fact that when I last taught, I was using assessment 5. Now there's assessment 6. So to prepare for this class, I had to do a little bit of updating, a little bit of reading. They're very thick reports, by the way. You can get them if you want. They're all downloadable or all readable online and all free. They're all very dense too. If you need something, if you don't want to take a sleeping pill. Okay. Now, one of Working Groups 1's responsibilities is to evaluate the likely amount of future climate change, the next roughly 100 years. And although this wasn't in the original syllabi, I'm now going to spend a little bit of time talking about how they do that. Now, how many people know what a partial differential equation is? A few. Okay. So if you take a look at the equations that govern the physics of the atmosphere, they're partial differential equations, and you can't get an exact solution for the entire atmosphere. So what they have to do is use computer approximations, numerical solutions of these equations. And to make things even worse for the people who know the mathematical techniques, even in that form, they're not solvable numerically. So they have to use parametrizations. So one of the things is you can think of them as very good approximations, but they're still approximate solutions. I remember in a workshop in Denmark, we had paleo climatologists, and that's what I do. And we had physicists who do climate modeling in the same room. And there's a big difference between the attitude of the two. A physicist got up and said, our computer models are based on the basic laws of physics. They are exact. And then a paleoclimatologist got up and said, that's BS. First of all, we know you can't hindcast a lot of events from the past. And second of all, these are all approximate parameterized solutions. So if you remember, this is the best we can do. These are our very best. I don't think in the IPCC climate modelers are the best in the world. We can't do any better, but they are still approximations. They're not exact. But what we have to do is this. So we take the globe and we break it up into a whole bunch of grids, squares. And then we look at average temperature, average average moisture, averages within that grid. So there's a typical grid, we're taking several hundred miles across. And then within those grids, then are made into boxes, which go higher and higher into the atmosphere. And then we start with the basic atmospheric parameters, temperature, humidity, and pressure, mass of the atmosphere for several heights. These are initial conditions. And then we take the basic atmospheric and heat balance differential equations and solve them numerically at each of the points to give the state of the atmosphere at some time in the future, delta T. So we start today, and then we go 6 months in advance, and then another 6 months in advance, and another 6 months in advance, another 6 months in advance, whatever, till you go 100 years into the future. You bootstrap. And if you've dealt with, a few people may have dealt with numerical solutions. So at least a few people knew what partial differential equations are. This is the typical way you do them, no matter what your problem is. So you keep calculating that until you reach the future time of interest, and you need supercomputers to do these calculations. They're very computer intensive. I mean, we do something like this when we make long-range weather forecasts. Although weather's harder to predict than climate. Okay, so now, as a paleoclimatologist and not a climate modeler, as I said, I want to emphasize that these are not exact. They're the best we can do, but they're not exact. And one of the things has to do with how do you test them? Well, you can calculate the climate in the past, right? Start today and calculate it in the past and see if your predictions meet the actual climate record. And when they first did that, they did a lousy job. So what they did is calibrate, refine. They said, okay, we're going to tweak the model until we can calculate the past climate. And well, they actually haven't done too badly at that. But you know what that means is you've calibrated it using the 120 years before they started modeling. So, you know, once you calibrate something, you can't test it against your calibration. You know, that's circular. Now, between 2000 and 215, we increased the amount of CO2 in the atmosphere by about 25%. And yet the observed temperature increase was smaller than that predicted by the computer models. Here's what the computer models predict. And here's what we saw. And so you can see a gap. And remember, when did I stop actively teaching this material? Well, probably about 2020. This was the temperature hiatus problem, and we discuss it quite a bit in class. Now, this is more recent data, somewhat more recent data, and you can see that now, up here in the yellow, we no longer have an underestimate. We now have, we no longer have the computer models overestimating the temperature increase. More recently, they've underestimated it. Now, I want to simply point out that they're not perfect. They're the best we can do, but they're not perfect. But if you take a look at the red line, which is our observation, and the black line, which is our computer models, so red, what we observe, black, what we predict, they're both going up. And actually, considering the difficulties, the computer models aren't doing that bad of a job. They're much smoother than our actual observations, but they still show the same upward trend. Any questions at this point? This is what our predictions are based on. Yes, we'll have to wait for the microphone.
Ed, earlier you showed the graph taking the percentage of parts per million of CO2 in the atmosphere measured from Mauna Loa.
Yeah.
That's right next door to Kilauea.
Yes.
Would that distort the data in any way?
I don't think so. For two reasons. First of all, you're going to get more, if most volcanic gases are dominated by sulfur, not carbon, sulfur dioxide. So basaltic lava flows probably don't give away that much CO2. And also you noticed how regular the graph is? The eruptions aren't nearly that regular. Having also, this is not the only place. I could have shown you data from Antarctica, for example. So there's several other places in the world where always remote spots. There's a place in the Amazon, always remote spots from human activity, and they all show the same trend.
That was my question. Thank you.
Yes. Any other questions? Okay. Well, we're going to, okay. But you have to do something else. Now, predicting, looking at the past climate, you know what the CO2 in the atmosphere is. But if you're going to do future climates, you don't know how much carbon dioxide we're going to put in the atmosphere or other atmospheric changes. So you have to, when you're predicting future climate changes, predict how much CO2 and other greenhouse gases are going to be emitted into the atmosphere. And that means you have to predict the future course of economic development. If we have a recession or depression, we're going to put less CO2 in the atmosphere, which is why what's happening now is really a climate change mitigation effect. Okay. Also technological innovation. Now, this is from when I taught. I just took this from one of my introductory classes. And in May 9th, 2016, there was one thing I was certain because my entire life had told me this is true. The Cubs weren't going to win a World Series. Okay. I just try to indicate how unpredictable things can be. So in order to get around the problem that we have to project, we have to know how much CO2 is going to put in the atmosphere, and that's going to depend on what technologies we use and what extent of how vigorous our economy is. The IPCC, they've changed the names of these, but now in the sixth assessment, they call these shared social economic pathways, SSPs. And each SSP has a different assumption about future economic development. But not only future population growth, how many people will we have? Technological innovation and energy use patterns. So they put all those things together and come up with different scenarios. And hence different amounts of greenhouse gas emissions. Here's an example. Here are what for our purposes will include the most important of these because they will be the extremes. SSP1 is the sustainability world. So we have a policy focused on sustainable development. So we're trying to decrease the amount of CO2 we put in the atmosphere. We have effective international cooperation. So governments the world around decide they're going to meet these goals. We have reduced inequality within and among countries, low consumption, and low population growth. So you put that together and you have the most sustainable world. That's one SSP. And the other SSPs are the ones up here. SSP5 to the left in red, SSP3. And those show the opposite. Let's look at SSP5. We've got policy focused on free markets, high consumption, still international cooperation, still reduced inequality. We have high economic growth and low population growth. So some good things. And then we've got P3, we've got policy focused on local security, barriers to international trade, high inequality both within and between societies, slow economic growth, low population growth in rich countries, high in other countries. So those are going to give us more carbon dioxide in the atmosphere. And now let's take a look at the results. Here they are. So are about midway between 2000, about 2025. And if we follow SSP1, you note that the temperature increase will level off and then begin to decrease slowly. SSP5, well, in that case, temperature is predicted to increase. And by 2100, which will be our benchmark, we're looking at more than 5 degrees Celsius. Remember, that's about roughly 9 degrees Fahrenheit, warmer average temperatures. So, you know, there's a wide range of possibilities depending on what we do. Now, which way do you think the world's headed right now? Okay. So what does that mean? First of all, and remember, these are predicted warmings, but predicted warming is not uniform. If you take a look, here's our temperature scale. It doesn't allow us to cool anywhere on this temperature scale, but the more redder and the more intense and the darker the colors, the more the warming. And note that it's not uniform. You can see the colors are patchy. That in lower latitudes, we have less warming. And in the continents, we have more warming compared to the oceans. So let's take a look at an example. So here's our simulated change at 1 degree Celsius global warming. So if our temperatures increase by 1 degree in 100 years, this is where they expect we will be. Now look at the equatorial oceans. So the equator runs right under the Horn of Africa, right here. Note that the oceans are will have a warming in the equator of less than half a degree. Equatorial land masses, again, take a look at the Horn of Africa and look up. It's a somewhat darker pink. The warming is between half a degree and 1 degree predicted. And the Arctic Ocean up here has a predicted warming between 1.5 and 2 degrees Celsius. Okay. If the average global warming is 4 degrees, there's the situation. You can see it's a lot darker. Just out of curiosity, we're there. So that looks like roughly a 3 degree increase. Multiply by 1.8, and you'll see that we're looking at a little over 5 degrees Fahrenheit in our average temperature. If we look at the equatorial ocean, now we have between a 1, again, right under the Horn of Africa, We've got between a 1 and 1.5 degrees Celsius increase predicted. Equatorial landmass, look at up from the Horn of Africa between 2 and 2.5 degrees. And the Arctic Ocean greater than 7 degrees Celsius. In other words, you're looking at roughly 12 degrees Fahrenheit. That will mean major changes for the Arctic Ocean. Major changes for my granddaughters, if they're still living in Alaska 100 years from now. The older one, I can't imagine living in a place where she can't ski or skate, but she may no longer be able to ski or ice skate in Alaska by that time. Okay, now precipitation is much harder to directly calculate. But first, let's look at what we know historically. This is the precipitation increase during the 20th century. If you take a look at the whole world, there's been an increase in the amount of precipitation, but it's not uniform. Note that take a look almost everywhere in the US, with a few exceptions, we have more rain than we used to have. But there are some places where we've had significant decreases. For instance, this part of the Sahara, Western Australia, that's the wheat belt in Australia. And these trends have continued into the early 21st century. This is a 20th century graph. Now, precipitation changes are very difficult to calculate directly. So the way they're usually modeled is to look at what has been the historical relationship between temperature and rainfall. So typically look at the history, and if you've got a warm year, how much does precipitation increase in an area? And just take a graph and get a relationship between the temperature of an area and the precipitation in that area. That's the usual way to do this, rather than go through the computer calculations. And of course, that means that if those relationships change, the models are off. Okay. So these are now our predictions. These are our projections. And the higher the temperature change, the greater the change in precipitation. Remember, as things get greenish blue, they get wetter. The darker, the wetter. As things get brownish orange, the drier, the darker, the drier. And so, for example, let's take a look at a 1.5 degree increase in the global average temperature. Precipitation in Holland is predicted to increase a little bit less than 10%. So it'll be a little bit wetter here. Maybe 10% wetter. While in southern Spain, it's going to be drier, but again, by around 10%. Look at a 4 degree Celsius change in global warming, and the projected change in rainfall in Holland will be 10 to 30%. So if it's up to 30%, that's a third more rain than we have now. And southern Spain, precipitation is projected to decrease by between 20 and 30%. So significantly drier. Or the wheat belt in Australia, also drier. I'm reading a memoir about the settling of Western Australia, the wheat belt. So that's why all these examples come to my mind. Okay, Now, soil moisture is the amount of moisture or water in the soil. And so this is what plants use to grow. Plants don't directly grab the rainfall. It comes up from the soil into their roots. So when you're looking at the growth of plants, it's soil moisture you really want to look at, not rainfall. And we have evapotranspiration, which is the loss of water to the atmosphere through direct evaporation and through the pores on the leaves and stem, mostly on the leaves, plants. Now, what happens to evapotranspiration when temperatures go up? It's more. It increases. So what this means is that soil moisture can decline even when the amount of rainfall increases. So if it's warm, the evapotranspiration can more than compensate for the increase in rainfall. And that's important because it's that soil moisture that's going to determine how much moisture is available for agriculture. For example, while the Great Lakes region and the Great Plains, both, and the Great Plains are agricultural belts, are predicted to have an increase in precipitation after a 1.5 degree increase in global temperature. So let's take a look at this. This is our precipitation change. And whether you're in Kansas or Michigan, you can have more rainfall. We're going to have no change in soil moisture here in Holland. So this extra 10% rainfall will be compensated for by increased evapotranspiration. And in the Western Great Plains, we even have a slight decrease in the amount of soil moisture, the amount of available for agriculture. By the way, where's our water coming from for most of our agriculture now in the Great Plains? Yes, it's groundwater. So now you have to irrigate because there isn't enough rainfall. And the problem with that is we're rapidly depleting that aquifer. This will make things even worse. Also note that the greater the change in temperature, the greater the change in soil moisture. So this is the 1.5 degree to the left. Okay, well, this is the 1.5 degree. This is a 4 degree change. And note that particularly in the Western Great Plains, get a 4 degree change, you're going to have a much larger decrease in the amount of soil moisture. Okay, so that's just some predictions. And I focused on those two things, temperature and amount of soil moisture and precipitation, because those are the most important things for human beings, right? How hot it is or cold it is, and how much water we have available for agriculture determines how good the environment is or how many people you can support in an environment. Now, note, climate change occurs naturally. Big lesson that I hope was clear from last class period. Climate changes. So one thing you can say about climate. Say one thing true about climate, climate changes on every scale, remember? On the scale of tens of millions of years, on the scale of 1,000,000 years, on the scale of 100 years, climate changes, always. In the climate, in the last 18,000 years, the average global temperature has increased by 6 degrees Celsius. Okay. So that's a big climate change. So that tells us one thing. Every plant and animal that is not extinct now was able to do what? Adapt to climate change. And some, of course, we do have things like the dire wolf, if you've been reading the news, that did go extinct. In the last climate change was too much for them, the mammoth, woolly mammoth. Although they had survived 18 climate changes of the same magnitude before. And so there was something special about the last climate change. Anyone have any hunting? That's one possible hypothesis. These mammoths, which had survived many climate changes and large predators dependent on them, did not survive the last one. And that may be because the last one was the only one in which human beings were able to hunt woolly mammoths. But anyway, we'll go back to that. Any plant or animal that could not adapt to Okay, for you who's watching at home, we're finished with the secret part of the lecture. Okay. How do they adapt? How do particularly plants, also animals, but how did they adapt to climate change? What did they do? They migrated. Strategy that most plants and animals use is to migrate. When it gets warmer, you either migrate to higher latitudes or higher altitudes. So you move. Now, there are minor strategies. You know, your genetic change makeup might vary a lot. If you've got, let's say, squirrels, it might be when it gets warmer, squirrels with thicker coats are at a disadvantage. So you can have minor changes within the genetic makeup of a population, but by and large, migration has been the way that plants and animals have adapted. Oh, okay. This was from my teaching days. And plants in particular don't get up and walk unless you are in a J.R. Tolkien novel. Individual plants stay in the same place, but they shift their range north and south, or higher and lower on a mountain slope by seed dispersal. And I don't know why. Oh, well, I must have cut that by seed dispersal. So by the movement of seeds. Now let's take a look at that. And I want to introduce the idea of a biome. This is the first concept I remember sticking with me from geography in probably fourth grade. Was the idea of a biome. We've got these large regional ecosystems within which we've many smaller ecosystems, but we've got the ecosystems of the tundra adapted to colder climates, of the taiga or the coniferous forests, the temperate deciduous forests where we are now. It's an interesting shape for Lake Michigan. And etc. So we've got these biomes, these broad collection of ecosystems adapted to similar climatic regimes. And in first approximation, what happens during changing climate conditions is that the biomes simply shift. the south or north, or if you're looking at alpine biomes, up or down. In detail, it's more complicated because the biomes change somewhat as they shift. Some plants and animals are more successful in the new environment than others, so they also change their makeup somewhat. But it's largely the movement of biomes that we're looking at. And here is an example. One of the things I've done is looked at cores, a lot of lake cores and a lot of bog cores. My work, remember, in paleoclimatology is to look at the changing environment along the Great Lakes. And I've been mostly interested in something called storminess. How much storm energy you have. So I would look in the peat bogs and I would look in the lake cores for proxies for storminess. So, and these are all based on lake cores. During glacial advances, the biomes compress and move southwards. So this is, and during glacial retreats, they expand and move northward. So it's actually a glacial retreat we're going to be looking at here. This is Europe. Look at the bottom. Look at the black and white figure up ahead. Look at the bottom. I don't know why my laser is not. Oh, there it is. Okay, so laser, look at the bottom. And you'll note that this is Europe 18,000 years ago during the last glacial maximum. And you'll note here's the continental ice sheet, which went down to about where Hamburg is. Stockholm, one of my favorite cities right there under ice. Then you had polar desert extending to probably about the Rhine Valley. And then Paris is in tundra. In other words, this was Paris in those days. Our polar bears wandering around the Eiffel Tower. And then when the glaciers retreated, this is the interglacial. This is what we have right now. Paris is in deciduous mixed forest. Stockholm is on the border between the taiga, the boreal conifer forest, and the deciduous forests. Tundra, way up at the border of the Arctic Ocean. So that's what happened. Here for North America, this is an aside. This is mostly due to work done at the University of Minnesota. The Swedes were the people who pioneered, among other things, the use of lake and bog cores to do paleoclimate work. And the University of Minnesota had connections with Sweden, obviously. So one of the people at the University of Minnesota went to Uppsala University, and he learned the techniques to do this. And he asked them, how long you needed a high quality microscope. And these are the days where a high quality microscope was, really fancy equipment. He said, how long can graduate students work? And this was told to me by an appalled Swede. How long can they work at a shift to do this work? And the person said, well, we'd never have a student work more than 8 hours at a microscope. So he bought a microscope, put it at the University of Minnesota, had his graduate students work in 3 shifts, 24 hours a day to do this work. And the Swedes were appalled that that's the way you'd force American students to work. But anyway, that's the way I had to work as a graduate student. Anyway, they did this work. And so this is what things looked like at the height of the last glacial. There we are under ice. And note that this right here is tundra or taiga, sort of mixed. And then as southern Ohio, tundra, ice retreats, now mixed deciduous forest. We're no longer under ice. We're at tundra or at that period, and it's kept that way. Now, this is a relatively hard diagram to see. I couldn't find it in color. And I looked for a better modern version and I could not find. I grabbed this. I even forget where, probably about 10 years ago. But this was the effect of global warming will be a shift of biomes. This is left is today, right is after doubling of CO2. And so let's take a look right here. This is our temperate mixed forest. Note that where we are right now with some temperate evergreen forest, that if we go after doubling CO2, Hudson Bay will be pretty much like the Upper Peninsula of Michigan. And some note here is alpine tundra. That will become fairly rare. There it is up here. The taiga tundra will shrink in some places completely disappear. So biomes will move northwards and those cold weather biomes will have a much smaller range. That's what would happen. There's a major difference between the last climate change, which remember was finished by 8,000 years ago, and the climate change today. A big difference, a major difference in the world. Worlds change so differently that we even now have a new geological term for the days we're living in. What has happened? What is major, the biggest change in the world in the last 8,000, 10,000 years? Human population. So the estimated population 10,000 years ago is 5 million people throughout the entire globe. And we were already dispersed throughout the entire globe by that time. We were already in North America. We were already in the Arctic. We were everywhere, except maybe some islands in Polynesia, that we are today. And there were only 5 million of us. Now, the population of New York City is a little more than 8 million. So less than the population of New York City. Our current population is now 8.2 billion people. And here is, this is our population projections for the future. Okay. Well, there's a lot of differences. And one of the main things is 8.2 billion people have disrupted all those migration pathways. Habitats are fragmented. So now, this is old growth forest in the United States. In 1620, estimated, top diagram. Here it is in, I think this is about 1950. And you can see that the amount of forest, old growth forest, has really fragmented. That migration pathways. If you are now interrupted by cities, they're interrupted by farmlands, they're interrupted by second growth forests with completely different mix of plants and animals. So it is now very hard for this ecosystem to somehow migrate, push its way up through all, through these farmers' fields, through suburbs, through cities. So habitat has been completely fragmented. And if it's not continuous, you can't migrate. And this is a point that I want to make, and this is one of the take-home points, is that climate change is not the primary problem. Habitat fragmentation is the primary problem. And that's true through so many things people attribute to climate change. Climate change is a straw that broke the camel's back. You take habitat fragmentation and then you add the actual stress of climate change, and you're going to create extinction, large amounts of extinction that you wouldn't have if the habitats were continuous. And again, that's true again and again and again. That it's not that climate change by itself is not going to cause the catastrophic things people say it is. Climate change plus all the other changes will. In addition to migration, people can adapt to climate change by technological and cultural changes. So we are an incredibly adaptable species. We're so successful it hurts. It's amazing. I mean, we've got human beings living in Antarctica and in tropical Africa, as far as you can get. Now, but I want to have a cautionary tale about human adaptation. We want to look at the Norse in Greenland. So Greenland was settled in 985 in 985 AD. By 1126 AD, that's what threw me, the AD was left off. It had a bishop and 4,000 people. It was a short 2-day sail from Iceland. And these people were pastoralists. They essentially were dairy farmers, is how they lived. The average male skeleton from this period was 5'7". So, a little bit less than it is today, but not that much. They're relatively tall Norwegians by those standards, those days. Now recall that we had the Little Ice Age that started at about 650 years ago and stopped about 150 years ago. And temperatures dropped. Here's our Little Ice Age drop on this chart here. And remember, this is the diagram I used. People floating outside of Amsterdam on a frozen river. Hans Brinker and the Silver Skates. Impossible anywhere except during the Little Ice Age. Now, by 1250 AD, the settlers in Greenland were complaining that there was too much sea ice. So it was harder to get to Iceland. And that fodder for cattle was becoming scarce. The last recorded contact with the settlers was 1408 AD. And archaeological evidence says that all settlers were dead, indicates that all settlers were dead by 1500 AD, and the last male skeletons were less than 5 feet tall. So that's a shrinkage of about 7 inches or more, with signs of severe malnutrition. Okay. Now, was Greenland depopulated? When no, okay, Janet. Okay, who lived there? Lived there? The Inuits. The Inuit people had no problem whatsoever adapting to the Little Ice Age because their way of life was adapted to colder climates. So they were able to thrive under the same conditions that the Norse wiped out the Norse. Cultural adaptations. Now, the Norsemen refused to give up their way of life, which was, cattle grazing. They were pastoralists. They refused to learn from the neighbors how to hunt seals and survive in other ways. Anyone here of Norwegian ancestry? A couple people. You have to remember, I'm Danish and Swedish. And so one of the things that I heard as a boy is would have said, that's typical of your Norwegians. You're stubborn Norwegians. Okay. And I'm sure Norwegians would have something to say about Danes in a similar fashion. Anyway, they refused to adapt, and so they went extinct. That culture was wiped out. One of the things we're going to have to do, climate change may cause mass extinction, may be very bad for a lot of the natural world. I'm sure human beings can adapt to it. It's going to be uncomfortable. We don't like changing our way of life. In fact, I think some political events show how much we dislike having to change our way of life. But we will adapt culturally. Now I'm going to look at some other specific consequences. Let's look at sea level, because that's something often brought up. What causes sea level to change? Okay, so the amount of water in the oceans, and water, if an iceberg melts, does it change the level of the ocean? No. So it has to be glacial ice on land being added. So yes, melting glaciers. What else causes expansion of water? Remember, until you get to 4 degrees Celsius, and then water's weird, but we won't go into that. The warmer your water gets, the more space it takes up. It expands thermally because those molecules are vibrating more rapidly. They push their neighbors aside, et cetera, and give us a greater volume. So thermal expansion is actually more important than glacial ice. The thermal expansion or contraction of oceans is the heat up or cool down. And we looked at some evidence last time that the sea temperatures are changing, and exchange of water between glacial ice on the land and the ocean. So those are two things that on the short term change our ocean levels. For long-term people who worked for folks like Exxon, who needed to look at sea levels over millions of years, tectonic changes, how deep the ocean basins are. But those don't change on the basis of thousands of years. Those take millions of years. And so here's the last glacial maximum. I always look at this, and I used to tell my students, look, during the last glacial maximum, I don't mention the fact they'd be under ice. During your spring break, this is how far you'd have to go to be to the ocean. Much. I'm sorry. Yes. So this is the At the glacial maximum, this is where the coastline was. Coastline, oh, I'm sorry. I just messed up. Oh, well. Okay, can you go back to tape and erase the last minute? Okay, the coastline 18,000 years ago, I'm sorry I was way out here. You'd have to go even further. Now, if all the ice sheets melt, this would be the coastline now. And so look, our students are going to be able to travel much less far for spring break. So look, for example, look how fat Florida was. Coastline, out 100 miles or so from the present Atlantic. Now, and sea level was 400 feet roughly below where it is now, 125 meters. And that's 18,000 years ago. So there's been an incredible amount of sea level rise in the last 18,000 years. Variations due to tides and weather make it kind of hard to estimate sea level. Even lake level for that matter. If you take a look at it, and we don't have tides, we simply have weather. So it's a hard thing to estimate, but the best estimates is that sea level has increased about 20 centimeters, about 8 inches since 1870. Well, and here are the predictions. We'll start with a baseline about 2020. And here is the projected sea level rises. And compared to the sea level change we've already seen, I mean, from that point, so you have to add 20 centimeters to all these to get the total one. They expect a further rise in sea levels to be between 20 and 100 centimeters, depending on which one of our projections is closest to reality. So note 100 centimeters is a little more than 3 feet. This is still small if you compare to the post-glacial change in sea level. Again, what's the difference? We live on the coast. So now we've got, in the past, as the coast migrated, so did everything else. Sometimes not completely. The barrier islands, Cape Hatteras, those were the beaches that, the beach ridges, the dunes, etc. And they're now isolated as islands because of sea level rise. They haven't been able to move back as far, but mostly the habitats just moved. But now we've got cities anchored there. And that is the problem. We'll have to move or fight the movement. And for several reasons, I mean, 3 feet doesn't seem that bad. I mean, even 3 feet, if it was just 3 feet, would not destroy Miami Beach, for example. But now, storm surges are one of the main hazards, destructive things on a coast, and that is not your normal sea level, but what happens when you have storms. Storms in which you've got wind that increases the waves and also blows the water, not only as waves, but as a bulge towards the coast. So increases in sea level increase the potential damage due to storm surges, which is that temporary increase in sea level due to strong onshore winds and low pressures. Remember, if you've got low pressures, it's like sucking on a straw. Water level comes up. That's one of the things that happens in a hurricane as it comes by. So, very few coastal cities, I think, can actually withstand, if they're close to the coast, the increase in storm surges. And some places will be just directly flooded. A 3-foot rise would flood 15% of the world's poorest and most densely populated countries. Remember, deltas are great places to live. Nile Delta, in this case, the Indo-Gangic Delta, the Niger-Congo Delta. All of those deltas are densely populated. And that's where, this is what a 1 meter, or roughly a 3-foot rise, all of this land is gone. And where else are you in a lot of trouble? Not as densely populated, but in deltas and islands, tropical islands, yeah. So some people will be simply flooded out. Other places threatened by storm surge. And people like to live by the coast. I once had the statistics at the tip of my tongue, but I think over half of the human population lives within 50 miles of the coast, and a lot of people on the coast. Okay. I didn't know how far I'd get, but now I want to look at extreme events. There are other typical events we could look at. We could have done a lot, but now let's just look at what we know about, because we've been looking at average conditions, except when we looked at storm surges. So extreme weather events, this is what we remember. I just watched a movie, Fellini's Amarcord, in which he's remembering his childhood. And one of the main things there is the year that they had enough snow in this northern Italy, Italian city that came up to the waist. That was a memorable event. It was that extreme event that everybody remembered from his childhood. So it's extreme events. And we're looking at things like heat waves, storms, cold snaps, etc. And extreme events can be as important in average as average conditions in affecting our lives. So I want to look at some of the extreme events. And by the way, this is all 5th assessment material, but I doubt if it's changed much in the 6th assessment. According to the IPCC, in the next 100 years, we'll have higher maximum temperatures and more hot days, very likely over nearly all land areas. So almost everywhere on land are hot. Our heat waves are going to be worse and more frequent. Higher minimum temperatures and fewer cold days and frost days, very likely over nearly all land areas. So very, very cold days are going to be less common. Now, think of my eldest granddaughter, and how, for her, this is going to be almost as bad as this. I mean, less days to be on skis. I mean, she's used to being able to be on skis 7 months out of the year. But certainly we won't be skiing at all here. And we're building an ice skate rink that's going to be harder and harder to keep the ice on. So here's summer maximum and winter minimum temperature changes. This again is 5th assessment stuff. Oh, this is Canadian from about the same time as the 5th assessment. And there is our average, so here's our average, these are our summer maximums. if we've got a 10-degree Fahrenheit increase at the top and a 5-degree Fahrenheit increase at the bottom. And you can see our summer maximum, if we have a 5-degree increase, is going to be close to 5 degrees. 10-degree increase, also close to 10 degrees, but that's higher, our maximum temperatures. So these are not our average anymore, but our heat wave temperatures are going to be 5 degrees Fahrenheit higher, or 10 degrees. And here's our winter minimum, and our winter minimum temperatures are also going to be higher. So those of you who hate those cold days in the winter may not find this completely unwelcome. Now the IPCC predicts more intense precipitation events, very likely. So we talked about the fact that we're going to get more rainfall, but we're going to get more intense, not spread out. But our rainfall, we're going to have more intense precipitation events. So we're going to have lots more rain falling in these events. But they also expect them to be less frequent. So in other words, we're going to have longer space between major precipitation events, but they're going to be more intense. So that does two things. Very intense precipitation events increases the risk of flood, and the longer times periods between precipitation events increases the risk of drought. So this will increase the likelihood of both floods and drought. And finally, hurricanes. Talk a little bit about those. Because every time you have a hurricane, people are blaming it on climate change. And I guess admit I find that a little annoying. What they do predict is that the increased tropical cyclone peak wind and precipitation intensities will probably increase. So you'll get stronger winds and more precipitation associated with hurricanes. Now, hurricane predictions can't be done exactly. What we know is you need a couple things for a hurricane. The warmer the water, the more likely a hurricane. So you need warm water. And there's no doubt, water temperatures will be warmer. But you also need a number of atmospheric conditions to form a hurricane. Temperature is not enough. You need relatively stable conditions in the hurricane forming areas. If not, the hurricanes break up before they form. And those are very hard to predict. But we do know that if you do have warmer water, if a hurricane forms, it should be stronger. We just don't know. What is much more difficult to predict is whether we'll have conditions that are likely to lead to less or more hurricanes. So they'll be stronger, but frequency is much harder to predict. And hurricane frequency is all over the place. If I ever got data like this, I'd just throw it out. I wouldn't publish the paper. There's just a lot of people say there's absolutely no evidence that hurricane frequency is changing or has changed. Just up some years, down other years. But on the other hand, as I pointed out, there is some indication that the strength or the power of hurricanes is changing. Well, what the IPCC decided that they suspect there may even be a decrease in hurricane frequency, but there'll be an increase in intensity. That's the prediction. And that's it, folks. This is the first time I've gotten to the end. I should go to the eye doctor every time before I give a lecture like this. I'm ready for questions.
Earlier today, you mentioned carbon 12 and carbon 13 and their changing presence in the atmosphere as being an indication that the carbon dioxide, the additional carbon dioxide in the atmosphere is coming from the consumption of fossil fuels.
At least some of it, yes.
Some of it. You didn't mention carbon 14.
Well, carbon 14 is produced in the upper atmosphere by
Cosmic.
by
radiation.
cosmic radiation, and then it decays. So as you produce more dead carbon, carbon 12 and carbon 13, you'll dilute the amount of carbon 14.
So that in a way strikes me as a more obvious explanation that the additional carbon is coming from fossil fuels.
Yeah.
Than the more subtle variation in 12 and 13.
Yeah,
So,
okay.
thank you. I
Yeah, you're welcome.
thought I was right, but I wasn't sure.
Okay.
Ed? You said 50% of the world's population lives within 50 miles of coastline.
That was my memory, remember?
I think that's pretty accurate based on other things I've read.
Yeah.
What strikes me, two things. First of all, much of our food supply is grown in the coastline areas, particularly rice, fruits, and vegetables.
Mm-hmm.
And secondly, where are 4 billion people going to migrate to?
Well, remember, within 50 miles doesn't mean they all have to move. But certainly the people in living exactly on the coast may. People in Miami Beach, for example, I don't see it being inhabitable if we have a 4-degree increase. But remember, well, you know what's going to happen. You know what the rule is in Florida. They're just going to pretend that didn't happen.
Well, until it becomes a mangrove swamp.
Yeah, the mangroves may be in danger. They'll have to move. And they are pretty much hemmed in right now. So it's not good for mangrove swamp. Yeah, I mean, coastal population will have to shift inland. And some cities may have to be abandoned. New Orleans exists, takes a large amount of resources to keep the city there, which we're keeping for historical reasons. 4-degree temperature increase, and probably we won't be able to continue to pour the resources into keeping New Orleans that we have. So go quickly. Or take your scuba gear and visit the French Quarter 100 years from now.
Good call.
Yes.
I was wondering if salinity, ocean salinity, has any weight or bearing in the hurricane piece and the density of the water with the glacial ice melting going on and the more fresh water pouring in?
Well, certainly salinity is important. I don't know, acidity of the ocean is changing because we're absorbing, among other things, CO2 creates carbonic acid. So more CO2 in the ocean water creates more acidic water, as does other changes in the atmosphere. I haven't heard much about changes in salinity, but as a basic principle, yes. And in fact, that's one of the explanations for the Younger Dryas. is that you had a sudden large amount of meltwater from Lake Agassiz flood the oceans, and that would create a lens of fresh water because it's less dense than salt water and won't sink immediately, and that would completely change ocean circulation. And now I'm speculating, but the more glacial ice you add, and glacial ice will be added to the surface of the oceans, you may decrease the salinity in ice, especially in high latitude oceans. I haven't heard much concern about that, but that doesn't say anything except about the things I pay attention to.
Also wondering if you have any comments about the Consumers Power Plants, been decommissioned out at Port Sheldon. And I've heard that they're looking at possibly recommissioning that. And that playing into, with carbon, with the coal and everything again.
I don't know. I do know this. Natural gas produces much less carbon dioxide than does burning coal. Just look at its composition. You produce much more water vapor, but much less carbon dioxide. I used to have my students in advanced environmental seminar. One of their topics was to take a look at whether an electric vehicle was good for the environment if you drove it in Holland. And if you take a look at not power generation and also how much CO2 you put in the atmosphere when you manufacture it, the answer was if you had an electric vehicle in Holland when we were still burning coal, you were hurting the environment. You were actually increasing the amount of carbon dioxide. If you had the same vehicle after we switched to natural gas, you were marginally decreasing the amount of carbon dioxide in the atmosphere. So how you generate your power is very important. I don't know anything about what's happening in Port Sheldon, whether they're going to recommission it, whether they'll be burning coal. In general, burning coal is worse for carbon dioxide emissions. If you're going to burn a fossil fuel, the best one to burn is natural gas.
Lastly, are you familiar with Catherine Hayhoe's work out of Texas? Catherine Hayhoe out of Texas Tech University. She's a climatologist there.
No, I'm not. Can you summarize it?
Well, she just makes all of this very accessible to the layman. She has a podcast and a website and things, and she's written some books. I highly recommend her.
Okay. Her name again?
Catherine Hayhoe, and she's a Christian climatologist.
And which do you know from where in Texas?
Yeah, Texas Tech, Lubbock.
Okay.
I know people who still do not believe in recycling. What can I say to them that they would understand?
Well, I'll
Why-
say, first of all, I'll say something about recycling, but of course it's a somewhat different problem than this. For the most part, what recycling does is limit the amount we have in landfills, and resource-wise, it helps alleviate shortages of certain materials. Things are getting scarce. Copper, for example. But a lot of and one of the things we can do to alleviate those scarcities, you can open more copper mines, but the problem is that we're exploiting the copper that's easy to get to. So to mine more copper, we're going to have to go and get it in ways that are more and more expensive and harder and harder. One of the things recycling can help alleviate that. Make sure that those things that can be used multiple times are used multiple times. It doesn't do much as far as climate is involved. It has a minor effect. I guess it will have some because it's probably much more energy intensive, producing more greenhouse effects if you're going to mine copper now than if you're going to recycle it. But I don't know what to say to them. I mean, I don't see what the argument is against recycling. I'd like to hear their arguments, except, I mean, I know my father didn't want to recycle, but I know my father didn't want to recycle because he didn't do it as a kid and he wasn't going to change. And so it, it was not a rational argument. Any other questions?
I've been reading in the National Geographic about the middle of South America, the Amazon and all that area below, that it is, if they disturb that area with industry, et cetera, they'll release tons of carbon CO2. What is happening there?
Well, I can just answer that in general terms. First of all, one of the main storage areas for carbon is the tropical forests. And so you get rid of tropical forests and you get rid of that major sink of carbon. One of the surprises is that in the past, it had been underestimated how important the temperate forests were. And we are actually seeing a greening in higher latitudes for all sorts of reasons. One of them is CO2 as a fertilizer, in a sense. So, you know, you put more CO2 in the atmosphere and you stimulate plant growth. And also but there are other changes as well. One of the things that shocked my students, we had an aerial, when I taught remote sensing, I'd have them compare the amount of forest along the coast in Allegan County from 1920 to 2020, and they were sure it was going to be less, but it's not, it's more. We have more forests now than we used to. So there's a greening in higher latitudes, which is acting as an additional sink of carbon. Let's hope it continues. But anything if we limit the amount of tropical rainforests, it's a problem. Anything that interferes with that.
Okay, I think we're past time, so if you have further questions, maybe Ed has time to stay a minute, but let's all give him our appreciation.
Well, thank you. It has been fun. But I'm also looking forward to being able to spend my week on something else than catching up with the 6th assessment. Anyway.